All right, greetings everyone. Welcome to the third part of the video for section 3.3, continuing on with our study of polynomials and the relationships between their formulas and their graphs and vice versa. And yeah, so let's get into it. So here we're going to work on writing a formula of a polynomial given the graph. And the instructions here tell us to use our knowledge of intercepts and long-run behavior to write the formula. So what we're going to start with here is just identifying the different intercepts. So we'll start by identifying the horizontal intercepts. So that says HI for horizontal intercepts. And as we identify these, we're also going to identify their multiplicities. So looking at our graph, looks like we have 1, 2, 3 horizontal intercepts. And we're not told what the variables are here, so we'll assume that they're x. We have horizontal intercepts at x equals -3, x equals -1, and x equals 2. And then recall, we can figure out based on what happens as the graph passes through that point, we can use that information to determine the multiplicities. So for example, looking at -3 here, notice that the graph passes straight through it. So there we know that the multiplicity there is 1. Okay. At -1, notice that the graph comes up, flattens out, and then goes through, which that tells us that this should be an odd power greater than 1. So it could be 3, 5, 7, 9, so on and so forth. And to tell the difference between whether this would be like a multiplicity of 3 or 9 or 13 or something like that, it's really hard. So we'll just stick with using a multiplicity of 3 here. And then at 2, notice that the graph bounces. It comes down, hits that point, and bounces back up. And again, from our study before, we know that that means that the multiplicity there is even. So it could be 2, 4, 6, 8, 10, 12, so on and so forth. But just to keep things simple, we're going to assume this is a multiplicity of 2. Okay, because again, it's really hard to tell the difference between 2, 4, 6, 8, any of those. All right, let's also identify our vertical intercept here. And it looks like our vertical intercept right here is at the point, I'm going to write down the coordinates here. Looks like that is at 0, 1. Okay. And now with this, we actually have enough information to find the equation of this graph here. And so, again, since we're not given a name for the function, I'm going to call it f of x. And we'll start by using our horizontal intercepts to write the equation. So for example, here we know that there's an x equals -3 is a horizontal intercept of the function. And thinking about what we've learned earlier, that means that there must be a term or a factor in our equation that is x plus 3. Now recall it's x plus 3, right? Because if we plug -3 in there, that would make this term equal 0, which is what makes this a horizontal intercept. And then also, we have that this 0 corresponding with this, the x equals -3, had a multiplicity of 1. So this is really like x plus 3 to the first power, which we could just leave as x plus 3. All right, going on to the x equals -1, that tells us that there should be a term of x plus 1 here in our equation. It has a multiplicity of 3, so that should be to the third power. And then finally, we have the x equals 2, which has a multiplicity of 2. So that tells us we should have an x minus 2 here, and then to the second power for the multiplicity. So we have x plus 3 times x plus 1 cubed times x minus 2 squared. All right. Now, you may think from looking at this that that would be our equation, right? F of x equals x plus 3 times x plus 1 cubed times x minus 2 squared. However, if you graphed this as is and compared it to the graph we were given, you would see that they are not exactly the same. And in particular, they would not go through the same vertical intercept here. Okay? So, how do we deal with that? Well, in any of these types of functions, there's always going to be a coefficient out front. Now, that coefficient could be a 1, which that means we wouldn't have to write it. But it could be something different, and so we have to find what it is. So I'm going to call that a. And then to find the value of a, what we do is we use a different point other than the horizontal intercepts to find that. And in this case, since we identified our vertical intercept, we can use that one. Now, you won't always be able to use the vertical intercept. It might be hard to identify or find the vertical intercept. But I would say that's often going to be your most useful point. And so what we do is we take that point, 0, 1. We're going to plug it in. So we know that it gives us an output of 1. And then we input 0 everywhere. So we have a times 0 plus 3 times 0 plus 1 cubed times 0 minus 2 squared. And we would solve for a, which in this case, it looks like if we did that, we would end up with a equals 1/12. Okay, and you can stop the video and double check how I got that. And then once you have that, you can just plug that into your equation from above. And we would have that our equation here for f of x would be f of x equals 1/12 times x plus 3 times x plus 1 cubed times x minus 2 squared. And that would be our answer. Okay? Now, one other thing we can check here is we were told to use long run behavior to try to determine what this function was. You notice that in our graph here, right, we have both tails going in the same direction. So it tells us this should be an even-powered function or even-powered polynomial. If we check from our work here, we have x plus 3 to the first, x plus 1 cubed, x plus 1 squared. If we multiply that out, the highest power we would end up with is x to the 6th, which is even, so this works. Okay? All right. Let's look at this problem. So now we're going to write a formula giving information in words. So we're told or asked to find the equation for the function v of t if v is a degree 5 polynomial with a root of multiplicity 2 at t equals 3. And then roots of multiplicity 1 at t equals 1, t equals negative 4, and t equals negative 7. And then our v-intercept is at 0, 2. Okay? So let's first start by using the information given about the intercepts. And again, this function is called v of t, so we don't need any x's here. So first of all, we're told that there's a root of multiplicity 2 at t equals 3, so that means we should have a t minus 3 squared. And again, it's t minus 3 because if we plug in the 3 there, right, that would give us a 0. So we have that. And then we also have multiplicity 1 at t equals 1, which will give us a t minus 1. T equals negative 4, which will give us a t plus 4. And then t equals negative 7, which will give us a t plus 7. Those are all to the first power because they're all multiplicities of root 1. Or, roots of multiplicity 1, sorry. And again, if we check the sum of our multiplicities here, so we have a 2, a 1, a 1, and a 1. Adding those all up gives us 5, which we were told from here is our degree, so we're on the right track there. Now, you may think we're done, but remember, there's this a out front we have to find. And to find that, we need another point. And here they've told us the v-intercept is 0, 2, which, just to reiterate, why is it called the v-intercept? Oh, right, because the output value here is 1, or v, excuse me. So that's why it's the v-intercept. So we'll plug in that information. So we'll say 2 equals a times 0 minus 3 squared times 0 minus 1 times 0 plus 4 times 0 plus 7. Could multiply all that out, solve for a, and when we do that, we would have, sorry, just doing this in my calculator here. It looks like we would get a is negative 1 over 126. So then our equation for v of t is going to be negative 1 over 126 times t minus 3 squared times t minus 1 times t plus 4 times t plus 7. And there we go. All right, that's it for this video. Thank you so much for watching.